And double check there's enough space. So you got all those things that we need to check. Okay, so we got plenty of space. And here is today's class. Okay, did anyone, actually spend any time on the documents that I sent you guys, or links of the documents that I sent you? No? Okay.
The Excel sheets.
Hmm?
The Excel sheets.
Yeah, no, not Excel, those are Google Sheets. Yeah, but they're spreadsheets, basically. I think those would be helpful because, that's the reason why I made those. So let's go ahead and take a look at those spreadsheets because I think it's going to be helpful for you guys to get some practice. Okay, so let me see. I need to sign into apps. Okay, so the spreadsheet is already linked from the class website. At the top of the class website, there's a link to the Google Drive that I shared with this class. So I'm just navigating to that same document. You cannot navigate to that that folder like this one, but what you should see is like this. Okay. There is a file called CNF generator. So let's take a look at this one first because I think this one is really good for practicing your resolution stuff. Okay, and I can see several people are logging in at the same time too. Cool. I think this is really cool. This is like a new teaching platform, where I can use a document that is stored in the cloud, and sooner or later, the rest of the class will only be looking at their own devices instead of me or the projector. They'll just be looking at their own devices, and I can see who's looking at the devices because of the camera on the device. Even though we are in the same room, we'll still need to rely on the Wi-Fi router and all the infrastructure to see each other. Just wait until the head-up display or the virtual reality thing becomes a reality. That will be even more fun. So we'll all be wearing those headsets in the same classroom.
Yeah.
Well, the thing is, if you do this, well, we can do that at home too. Except when you can do it at home, most people won't do it because they got better things to do at home. All right, so this is a really kind of, I like it, because I made it work. So the way you make this work is, it will give you some kind of random. It's not entirely random, okay? There's a certain structure to it, but it's sort of random. So it'll give you a CNF like this one. The exclamation point is the same thing as a not. The plus is the same thing as an or. And then when you look at the parentheses, the so-called multiplication is the same thing as a conjunction. So when you look at this particular cell B1, it is a CNF. And this is already telling you that it should resolve to a contradiction. Okay? So that means, as an exercise, you can practice your resolution steps so that you can see whether you can make this resolve to a contradiction or not. If you need a different example, if you need something else to practice on, just, do some updates, okay? Just do an update here, and it will give you a different example. And this one resolves to a contradiction as well, and there will be some ones that you cannot resolve to a contradiction, like this one. This one will get stuck and not resolve to a contradiction. In other words, there's no way to resolve this to a false. And this whole thing is just randomized. There's no kind of real systematic way of generating these CNFs, but it works. So this is good for practice purposes, because if you need some additional ways to practice, how to do resolution, this you can use this to help you, kind of get the resolution steps down. Okay. Any questions about this? I'm not going to grade this. Okay. There's absolutely no way I'm going to grade this. If you want to use this, the first thing you need to do is to make a copy of this file, so that you can actually make changes to any cell. And then once you can make changes to the cells, then you can go ahead and it will update the CNF itself, and it will figure out whether the CNF is resolvable or not, or can it be resolved to contradiction. Okay, so this is only the first page. For those of you who want to kind of understand how everything works in the back end, the second sheet is going to show you how everything works. There's no need to understand this particular sheet, okay? But if you do take a look at this one, it will help you really understand the whole point of resolution, and and also and you can also tell how the spreadsheet itself can tell whether the CNF will resolve to a 0 or not. Because the spreadsheet doesn't do resolution, it has a different way of managing and figuring out whether there's a contradiction or not. So that's something that you might want to look into, is the mechanism of the spreadsheet itself, because that will also help you understand, what do we mean by a CNF and stuff like that. Okay, so this might be something that you want to look at. I made another spreadsheet. It has to do with relations. I'm hoping you guys do remember relations, because that's going to be in the exam. Okay, so in this one, you can basically figure out the relation. If ARA is true, it is represented as this particular cell as a true. If BRA is true, it is here. If BRC is true, it is reflected here. In other words, it's a very small example. It only has 4 elements in this particular set, but by tweaking the true and the false, okay, you can then use the spreadsheet to tell you whether it is reflexive or not. Is it symmetric or not? Is it anti-symmetric or not? Is it transitive or not? And then from those, it will also tell you whether it is equivalent or not. It will tell you whether it is partially ordered and also completely ordered. Okay? So the way it works is it basically works out all the combinations of the ABCD. These are basically column number and row number. Column number 2 is corresponding to A, and then row number 2 is corresponding to A as well. So basically, I'm using these to represent the individual elements in the set, and whether this relates to this one, or excuse me, the other way around, whether this relates to this is indicated here. It's just spelling it out. Instead of a table form, it spells out all the possible relations, and then whether something is reflexive or not is the answer. The answer is over here. So in this case, it is not reflexive because there's a false here. CRC is not true. Now, if you change this particular cell to a true, then it's reflexive. So by tweaking this thing, you can now generate cases where, okay, can I make it not reflexive but symmetric? Okay, you play with it and see how you can do it. Or you can come up with a matrix itself, okay, and then you can try to answer the question: is this reflexive? Is it symmetric? And so on. So you can use this spreadsheet in many ways. Okay, you can hand edit a particular table to a certain goal, or you can randomly generate a table and then try to figure out does it have these various properties or not. Is that okay? All right. So I find this I'm hoping this will be useful, because it's not just being able to verify the properties of a particular relation, because when you look at all the beige color cells, those are all answers that are automatically computed by the spreadsheet itself. But if you look at how these equations are done, if you look at the actual formula in the spreadsheet, that will also help you understand what does it mean when we say reflexive? What does it mean when we say symmetric, and so on? Because each one of these cells is a particular computation. Now the thing about indirect and address, you can look it up, okay? It's a spreadsheet function. Address basically composes a cell reference out of 2 numbers. If you give it the row number and the column number, it will generate quote unquote an address, and then indirect is dereferencing the address. So by using these 2, I can make a particular formula, use the value of any particular cell in the spreadsheet based on calculations. So that makes it very flexible, okay? But that's the whole point, because in this case, I'm just figuring out in terms of reflexive. Okay, let's take a look at reflexive one. It's basically saying if B9 does not equal to C9, don't do anything. because if these two are the same, okay, are not the same, sorry. If these two are not the same, then reflexivity has no meaning for that particular pair, so we will just say this cell is true. What if they are the same? Now, if they are the same, then the only way to make this OR true is the second part, which is, oh, then we have to actually see whether, that particular cell has a value of true or not. But these are all the diagonal elements because you have this column number and the row number being exactly the same. Okay, so by looking into the spreadsheet and looking into the formula in the spreadsheet, that also may help you understand, what does it mean to be reflexive, what does it mean to be symmetric, and so on. The most important point is, in order for something to be reflexive, all of these have to be true. If you look at this equation, it is a and it specifies the range of cells that has to be true in order for this cell, or cell 25, E25 to be true. Then the cells E9 to E24 as a range, they all have to be true. Is that okay or not? I know this is not a spreadsheet class, it's not a CISA 311, 312 or something like that. I don't think in that class they would introduce address or indirect. But it is still a spreadsheet that you can use. Okay, if you don't want to read into the equations or the formulae in the spreadsheet itself, it's okay. You don't have to do that. But at least this gives you a tool so that you can say, okay, I'm presenting this particular relation. Okay, what are the properties of this relation? This at least can help you verify that part of the understanding. Okay. Are there any questions about the purpose of these two spreadsheets? Yep.
What is the column H that you have?
Column H?
I see that you have a.
You mean this one?
Yeah. What's the term it falls under?
It's under trichotomy. Trichotomy basically says for any pair of relations, you need to have one and only one R. So given A and B, then you have to say, A, R, B, or exclusive or B, R, A. That is trichotomy.
So we need to know that for this one?
You need that to define what is fully ordered, completely ordered, because we get partial ordering and then we also get complete ordering. So, okay, let's take a look at how this cell is utilized. This particular cell is only used in this one. So when you look at what is being totally ordered is referring to F29, which is this one. So in order for something, for a relation to be totally ordered, it has to be partially ordered first. Okay? But then it also relies on H25, which is trichotomy. So in order for something to be totally ordered, it has to be both partially ordered and also has trichotomy applicable.
What do you mean by partially ordered?
Well, click it and find out, right? That's the whole thing about this spreadsheet. It is kind of an alternative way to represent all of these properties. Okay, so when you click on this one, you can look at the equation. In order for something to be partially ordered, it has to be E25, which is reflexive, G25, which is antisymmetric, and E59, which is transitive. So that's how you can read a spreadsheet like this, because the actual equations, you can read it. This is like completely open source. There's no magic behind the scenes. So by looking into how the equations are defined, that really kind of helps you understand, oh, okay, so this is what it means to be symmetric. This is what it means to be transitive, and so on. So transitive has its own table, because in order to check whether something is transitive or not, we need to pick 3 elements from the set, right? So when you have 4 elements in the entire set, how many ways can you choose 3 where it can be the same thing? 4 times 4 times 4. So you got 64 possible ways of choosing things. So that's why we have a pretty gigantic table here with 64 rows, and then each one is representing, oh, what if I choose, in this case, B, this is D and E, okay? So it's basically looking at, is B, R, C, and then C, R, D, if those are both true, and then B, R, D is also true, then this row is a true. So when you look at that, I know it looks kind of difficult to read, but you can read this part. It says, okay, can you guys see what it says? Okay, if I click it, it's easier because it's color coded. There you go. Does that make it easier? So you have a, I do not have implication, so that's why I have to use a negation and an or. I'm using that to mean implication. So the and is basically what you need. It's basically saying, C84 has to relate to B84, B84 has to relate to D84, okay? And then the other part of the disjunction, which is this part over here, is basically asking the question, is C84 relating to D84? If the implication holds, then for this particular case, it is transitive. But you need every single combination to meet this requirement for the entire relation itself to be considered transitive. So that's why when you look at the equation all the way at the bottom, which is this one here, it is looking at the previous 64 cells and ask, are they all true? Because if any one of those things is false, then you do not have transitive anymore. This is corresponding. Okay, so this is a good time to basically remind you what this is. This is basically saying for all A in the set domain, for all B in D, for all C in D, ARB and BRC, oops, BRC implies ARC. It's basically representing exactly the same thing, but using spreadsheet formulae. Is that okay? So, for some people, this may be more helpful, in terms of explaining, the definitions of those terms. For some other people, this may be, kind of more distracting and it's not helping. So, you can choose whether to look at a spreadsheet or not. Okay, it's just a resource out there. If you think it might be helpful, use it. If you think, this is making things more confusing, don't look at it. Is that okay? All right, cool. All right, so this would be a good time. Oh, I like this special icon. Anonymous Nyan Cat. And what is that? A chipmunk. And this one is an armadillo. Okay, that looks like an armadillo to me. Okay, cool. All right, are there any questions about these two spreadsheets? One on relations and the other one is on CNF. Okay, all right. If there are no questions about these, then we can go ahead and work on the homework assignment because it's due today. Right? No? No? Okay.
We can work on the homework.
Okay, so you guys do have to work on that. So in that case, the other one, this one can be helpful, because this one can help you kind of do some exercise on resolution. Are there any questions about resolution then? Yep.
How do you do resolution if you have like 4 letters?
When you have 4 letters?
In all examples you have just 2 letters, pretty much they're canceled out.
Well, let's take a look at this one and we'll use it as an example. How about that? So this one does not resolve the contradiction, okay? So there's no hope for this thing to resolve to a 0, okay? So we know this ahead of time because of the spreadsheet. So we'll go ahead and copy this into a notepad, and then I'll use the notepad to work on this, okay? All right. Okay, so the whole thing about resolution is you just have to pick out two clauses. Okay, each thing in parentheses is called a clause. It is basically a part of a CNF. What you need to do is to find one clause that has the non-negative variable, let's say p, and then the other one has to have the negated version of that variable that you want to use. Now, which one you want to use for resolution is entirely up to you. So in this case, I'm just going to randomly picking this p is going to be annihilated by this not p over here, and as a result, these will be joined by conjunction. Okay, so we'll see what's going to happen here. Okay, so the first thing I do is I copy and paste the original thing, because we are not going to lose anything when you are resolving. We're just adding additional clauses, and those additional clauses are already implied by the existing clauses, so they're not adding any new information to the whole thing. So this is going to be a new clause by using p as the resolving variable. So in this case, we'll copy what is left of the first clause, and then what is left of the second clause, but I need the plus sign over here. And you can see that it's not going to be very helpful in this case, because when you see something like this, you can just rearrange things a little bit. Okay, so we can rearrange and put this over here, and that's enough to illustrate that this clause is not useful, because I can now go to the next line and simplify this and just say, hey, what is this? If I just focus on this part, what is it? Q or not Q? Is a 1, right? It's a true. Okay, so we put a true over here. True or blah blah or blah blah or blah blah or blah blah. Okay, that makes the whole thing true, right? Okay, so we'll do this and just say, oh, that would turn the entire thing true, and then so we now end up with an and true at the end of the original CNF. What is that doing? Absolutely nothing, which also means that, hey, we don't even have to write it. So we got back to the original CNF, because the result of this resolution basically doesn't serve any purpose. It's nothing new. It just gets removed. Is that okay? So let's pick something else. Let's pick. Let's see. We can pick. Try to pick something that will resolve to something that's new. Okay, that's not going to be helpful. There may not be anything that is actually, sorry? Yeah, I don't think there is, because they just have, one has the, it's still,
Not T, not R, and S.
Okay, which two clauses are we resolving?
The third clause and the fourth clause.
The third and which one?
The fourth.
These two? So you have to be using S as the resolving variable, right? Because this one has the non-negative version of S, this one has the negative version of S. So do you want to do that?
It's gonna be scary.
Yeah, it's not going to be helpful, because this term is more specific than this term of here, and by annihilating S here, it's just going to be, well, it's still going to be useful, because it's not going to give you a true, so it's still going to be useful. Okay, let's go ahead and do this one. Okay. So copy, paste, and then what we do is we resolve these two clauses and see what's going to happen. So we'll concatenate everything other than the resolving variable. So I'm going to do this, even though it seems like it's just a waste of time, we're going to do it. Now you can see that the non-negated S here and the negated S here are gone, because that's the resolving term. So we have this left. Okay, that's the first line, and I can do some manipulation here. Now this one is not useless. Okay, this one, by the way, oops, move it over here, and then we have this one, and we can put it next to here. There we go. So now it seems pretty obvious that we can do some simplification, because not P or not P is just not P, not R or not R is just not R. So in the next row, now we can say, oh, we can simplify this a little bit. So we can get rid of all the extra stuff that is not needed and make it this. This is actually productive because this is not something that is already in the 5 clauses that we started off with, and yet it is not trivial, it is not true. So we did end up with something that's useful. That was a good one, good pick. But at some point you're gonna be stuck, okay? At some point you're gonna be stuck and say, no matter what I do, no matter which 2 clauses I resolve, and no matter which variable I use as the resolving variable, it's still not going to produce anything useful. So at that point, you can say, okay, I'm going to give up because we cannot do any additional resolution anymore. Yep.
Are you allowed to use a resolved variable with an existing one? Like, can you use like the one we just created with
Yes.
not P, not RS?
Yes. It is now a part of the pool, but remember, you cannot resolve 2 variables in one shot. You can only resolve with 1 variable each time. So which, do you want to do one more step? I mean,
Well, no,
you
because
can,
then there can't then, right?
I don't think we can do much more.
There's no resolvable variables. If I add those two, I'll just end up eventually I'll end up with the not P, and not R, and S and Q.
Right. I don't think we can. I don't think there's really much to do. I may be missing some, but because what you really want to look for is you only have one single variable that is differing between the 2 clauses, and then the rest of the clauses are completely different. That would be ideal, but we don't have that situation here. We have a lot of negation of variables here. You can resolve. You can resolve these 2, right? I mean, these 2 are pretty easy to resolve because they just resolve to P plus Q plus R, right? Because I'm using this non-negated S here to resolve with this negated S. So we end up with just P plus Q plus R, P plus Q plus R, but that simplifies to just P plus Q plus R, which is missing at this point. So we can go.
That's gonna cancel itself out with the not P plus
Yeah.
They'll cancel each other out.
What?
With the variable.
The 2 last terms.
The one right next to it.
Which 2?
The last 2.
The last 2? These 2?
They now cancel each other out.
No. You can only use one term to resolve. So are you going to use the P term to resolve? Are you going to use the Q term to resolve? Or are you going to use the R term to resolve? Pick one.
Whichever one you use is going to end in true.
Okay, so these 2 resolving will only end up with something that is trivial. Okay, fine.
They'll all go away.
No, it won't all go away.
Yeah. If I use the R,
Yeah.
and then go ahead and go through it, then the not P, then the R.
The not P or P will become a true, and then the entire thing becomes true. But you cannot take this away. These 2 cannot be taken away. Do you see what I mean? Because any clause by itself that does not turn into true or false cannot be removed from the CNF. If an individual clause becomes true, yes, take it away. If an individual clause becomes false, you got the answer, right? But if it is neither, then you have to leave it in the CNF. Is that making any sense?
In my mind, when I'm resolving it, it seems like it works as just true.
It becomes true. The new term becomes true.
Yeah.
But this one is not true, right? The one that I'm highlighting right now is not true. It's not false either.
Not alone.
Yeah, so you cannot get rid of it. Now, on the other hand,
But the
if
new
it
term
does,
created from using those 2 will be true, and then that will just eliminate itself.
yeah, but that means you just don't use these 2 to resolve each other. They might still be useful to resolve something else.
That makes sense.
Okay, so we can see if there's one term here that they can use to resolve and it's still useful. PQR, no. We're looking for something that's only different by one single term, but we used this one already. Yep, there's not much you can do with this one. Question? Yep.
Going to the resolution lecture notes, because there was the example you showed where you weren't able to resolve a particular CNF.
Yeah, I can do that. But before we go, are there any questions about this particular example? Yep.
So on the exam, you want us to just add a new term by just doing the conjugation thing?
The conjunction?
Conjunction?
Yeah,
So-
you have to indicate what is the new term being introduced and how you got the new term.
So you want us to underline it or?
Use whatever way that you can let me know I'm using this clause, and this is the variable that I'm using to resolve it. So there are three things you need to let me know. Which two clauses? This is the first clause, this is the second clause. Out of the clause, which variable are you using for resolving? Whatever variable you're picking, it has to be non-negated in one of the clauses, one of the two clauses, and has to be negated in the other clause. So you have to indicate how you chose. Yep, go ahead.
For the homework, did you want us to just do what you just said? Or did you want us to include how we solve?
Because in the homework you're using the HTML editor, copy and pasting is easy. So I would just go ahead and, if I were you, I would just copy and paste it and use some kind of marking to indicate this is the first clause, this is the second clause. You can use color, okay? Because I'm not colorblind, so I won't use the accessibility thing and say, what are you guys doing to me? I cannot see your answer. So, you can use color coding, you can use underline, you can use, any type of marking to tell me, okay, this is the first clause, this is the second clause, and then within each clause, identify which variable you're picking for resolving. Because in some cases, there are multiple choices. Is that answering your question too?
Just also, did you not want us to add like what kind of law we use to?
Other than, annihilating, and getting true, like this one here, other than, combining these two into a true and then eventually canceling out the entire thing, there are no specific rules to apply in this case. It's just really resolution. Okay. Any other questions? Yep.
Is it possible to reach contradiction without two single variable conjunctions?
I don't think it is possible, because if you have two clauses where at least one of the two clauses has two variables, when you annihilate using the one that is resolving, the resulting will still have one single variable, cannot be empty. So the only time you can get to a contradiction is the two clauses that you choose are single variable clauses, where one is a single variable, the other one is the negation of that one single variable, and each one is a standalone clause in the CNF. That's the only time you can reach a contradiction.
Okay, so if we looked at this problem, we would just immediately.
Oh, this one is not resolvable. We already know it's not resolvable.
Right, so it's not worth.
Yeah. But you can pick one that is resolvable. Just keep changing this value here, and this one cannot be resolved. Yeah. How you change this? Okay, this one is resolvable. So with this one, eventually you should be able to resolve to a 0. But I'll leave it to you guys to kind of do this as an exercise. Yes.
I'm fine. You answered my question.
Huh?
You answered my question.
Oh, okay, cool. Yep.
It's actually like 3 steps.
Sorry?
It's not that many steps.
Well, I think this R can be used to annihilate, this R can be used to get rid of, no, this one has a P, so I would use this R, not R first. On this one, then you have P or Q left. Then you have P or Q left. Well, I'll leave it up to you guys to do it. But that's the whole point, right? But how do I know this one has to be resolved, will resolve to a contradiction? Because of the truth table. Because in the raw part, I basically worked out each individual clause, and eventually it will resolve to a false. Yep, so this one is corresponding to this. did that happen? I might have a bug in the spreadsheet. I'll have to fix it. I'll have to double check and see if that is the case. Because if an entire row is missing, that might turn into a contradiction automatically. That may be a problem. Yep, I think I can see a problem here. So I have to go back and check on this one. All right. So somebody wanted me to go back to the CNF notes.
The resolution.
The resolution one? Okay, let's go ahead and do that. Okay, wrong class. Okay, so you want to take a look at resolution? Here we go. Okay.
So in the example where you weren't able to resolve it, scroll down below.
I cannot resolve, right? The first one?
Yes.
Yep. Okay.
You went on and took another theorem to conjoin with the CNF that you had before, and then you were able to resolve it. Did you say that proved the previous theorem that you weren't able to resolve?
Wait, hold on a second here. This one does not resolve because at this point there's no. You can try all you want, it won't come up with any new terms. Right.
And in example 2, you used a different CNF expression to join with that.
Right.
Yeah, and you said that example 2 proved example 1. Or were you just illustrating a different example that actually resolved?
This one is a whole different example because when you look at the starting point of those two, they are different.
Right. I thought you used like a different theorem to prove example.
A different theorem, correct.
Yeah.
So in the first one, the theorem that I was using was R implies Q. That's the original theorem.
Right.
But you have to negate the theorem first before you put it into the CNF. In the second example, the theorem that I want to prove is R implies P instead of R implies Q.
Right.
And that turned out to be a theorem in this case.
I thought example 1 and 2, you wanted to relate them. So never mind.
Well, they are related only because the three premises are the same.
Right.
So they basically use the same premises, but the theorem is different.
Resolving example 2 doesn't imply anything about theorem in example 1. Right?
It does not say anything about example 1. That is correct. So because in example 1 we get to a point where we are completely stuck, but we cannot get to a contradiction, that means the original theorem that we are proposing, which is R implies Q, is not a theorem. It cannot be implied by the stuff that is in iota. Is that okay? All right. Any other questions? No other questions? This is okay? All right. All right, so with this out of the way, and you still have your homework to do, we can continue to talk about probability, or are there any further questions about resolution or propositional logic or relations? Questions? All right, that's a good answer. Not only is there no question, I'm bored. All right, so last time we talked about combination and permutation. We talked about lottery and stuff like that. So this is really kind of useful, important stuff because it can be used to solve a variety of problems. Are there any questions about permutation versus combination and when to use which one? The key to both of those is without replacement. You select something out of a pool, but then you take it out of the pool so that the next time you choose something, whatever you choose out of the pool cannot be put back into the pool to be chosen again. That is when permutation or combination becomes useful. Permutation is useful when ordering is important. Combination is useful when ordering is insignificant and it is not used, or it simply does not make a difference. Is that okay so far? With all those terms?
It's like
Okay.
going back to like the lotto.
Sorry?
Like this goes back to like the lotto.
Going back to the lotto. So in the case of lotto,
Like ordering
it's a
orders.
combination because ordering of the numbers does not matter. Okay.
Permutations were like finding the password on a keypad.
Correct. In the case of a password, then permutation is useful, but you may not want to use permutation either, because in the case of a password, you can't use the same letter or digit again. So unless you put a constraint on your password, not being able to use a digit or a character more than once in the password, then it's not permutation either. Okay. Are there any questions about this? So I'll give you a scenario. Okay, I'm gonna write it down so that we can actually see it, because I wouldn't be able to remember what I said. Okay. So Jack is planning for family vacations. There are 20 dream destinations. So there are 20 things to choose from, right? Okay. In each year, only the same destination can be visited only once, up to once. In other words, out of the 20 dream destinations, you may not get to all of them, okay? But whatever you choose, you can only go there exactly once in that 1 year. Okay. So the question is, how many ways can Jack plan trips when there are, I don't know, like 5 trips in 1 year? Okay, so if this is the question, what are you going to ask? First of all, do we have that requirement of without replacement? Once you have chosen a destination as the first trip, can we use that destination again? No. So it is without replacement, which basically means, permutation or combination. Pick one of those two. Is that making any sense? But how do we choose, whether it is permutation or combination? Is ordering important, right? So what do you think? Do you think ordering is important or not? Okay, so the question is ordering important? Okay, so I'll give you 2 extreme cases. Alaska in the winter and, I don't know. Let's pick a hot place. Okay, sure. Death Valley in the summer, as opposed to Alaska in the summer versus Death Valley in the winter. Do you think it will make any difference to the family members? Yeah. Do you think it would make any difference in terms of how much it would cost? Absolutely, right? Who wants to go to Death Valley in the summer? Well, people with a death wish, I guess. But going to Alaska in the winter, is not probably a very good idea either. So ordering is going to be important. So you need to ask that question: is ordering is that important? So in this case, it is important. Okay. So ordering is important, which means what do we choose now? Permutation. Excellent. So permutation, what are we choosing out of? What is the number of options to begin with? 20, and out of 20 we are choosing 5. That's it. So this is the total number of possible ways to arrange the 20 dream destinations, but choosing only 5, and considering all the ways of arranging the ordering of those 5 destinations. Is that making any sense? That turns out to be a pretty big number, by the way. Okay? So we'll take a look at this number and see, okay, but how big is that number? since we have some spreadsheets up already, we can just go ahead and use this spreadsheet. Okay, this is for the next class, but I'm gonna just borrow the spreadsheet to do one quick calculation here. So this is permutation, permut. Okay, there we go. Permut 25, and that turns out to be a pretty big number. It's 1.8 million, 1.9 million ways of arranging it. Good luck, Jack. See you next year. But is that making any sense? Because out of the 20 destinations, you have 20 possible ways to choose the first destination, 19 to choose the second, 18 to choose the third, 17, and then 16. So you have to multiply these numbers. That turns out to be 1.86 million or so. Is that making any sense? Okay, and the order of magnitude matches too. So I'm pretty sure that is the correct number. What do you think would be a case where ordering does not matter? Lotto is one, okay, but can we find some other examples where ordering does not matter?
Poker hand.
Sorry?
A poker hand.
Poker hand, okay, so in a poker hand, ordering does not matter. Okay, very good. Anything else? Yep.
Dice roll.
A dice roll, but dice roll is not without replacement. In other words, if you roll a dice, okay, let's say it's a 6-faced, die. When you after the first roll, you cannot tape the side that is showing, and say we cannot use that number again. So that would not be a case, to use permutation or combination. Is that making any sense? Okay. All right, so let's go ahead and answer another question, okay? I think this class right now has about 40 people in the classroom. So I'm going to go calculate the chances of there are no 2 people in the class with the same birthday. Everybody has a unique birthday in this classroom. Okay, so what are the chances that out of a class of 40, everybody has a unique birthday? No 2 or 3 people or 4 people have the same birthday. Okay, let's do that calculation. Yep.
Doesn't it cap off at like 32 or something like that?
It doesn't quite cap off because ideally speaking, you can have a class of up to 365 people and each one has a unique birthday.
That's true.
So that would be your actual cap. But the chances, does decrease very rapidly that you will have a class without duplicate birthdays. Okay, so we'll go ahead and check, okay, with 40 people in the classroom, what are the chances that every birthday is unique? Okay, what do you guys think? Do you think it's a pretty good chance, or no, it's a very slim chance that that's going to happen? Okay, so let's try to figure out. So how do we approach that problem? So let me write down the problem first so we have something to focus on. Okay, so we'll scroll this out and then write a new question here. Okay. Of a class of 40 people, what are the chances that all birthdays are unique? Okay, so that's the question. What do you think? First of all, we have to ask the question, does it have anything to do with without replacement? In other words, if I tell you that my birthday is April 1st, okay, can you have April 1st as your birthday?
Yes.
To meet this requirement?
No.
Okay, so is it with or without replacement? Without replacement. Okay, so if it's without replacement, we can now say, okay, is it combination or is it permutation? Yeah, right? Okay. All right, so is it with or without replacement? It is without replacement. Is ordering important?
No. That's combination.
Okay, so we got 365 days in a year. Okay. of which we're going to choose 40. So, okay, that's an easy one. This is just a combination. You have a set of 365 days, and then you choose 40 elements out of those 365 elements in a set, and that set is representing the number of days in the year. Okay, so we have this number here, but then the question is, out of these 40, how many ways can we arrange it? It'll be 40 factorial. So ordering is important. Because when you multiply this by 40 factorial, what do you think you get back? If you look at this entire thing, that's the same as what? The permutation of 365 choosing 40. Because ordering is actually important. Sorry? It's a pretty big number, yeah. Yep.
Why do you multiply by 40 factorial?
Okay, so let's just say that the class only has 2 people, you and I. Okay? We choose the 2 days out of the entire year as April 1st and April 2nd. If I'm born on April 1st, then you're April 2nd. If I'm born on April 2nd, you're born on April 1st. But those are 2 distinct cases. The 2 separate possibilities of distributing those 2 birthdays with a class of 2 people. So that's why ordering is important, because it has to do with who has which birthday. So in other words, I can easily pick out 40 days out of a year. Okay, so I start with a stack of cards. Each card is representing a day in a year. I pick out 40 of those, and I just randomly distribute those cards to the entire class. But who gets which card makes a difference. And that's why ordering is important. Is that okay or not? April 1st and April 2nd, right? Okay, so let's say this is tag. Okay, so tag is choosing April 1st. Okay, and this is Jack. Okay. Okay, and Jack is picking April 2nd. This is one possible outcome, right? If I have a class of only 2 people, this is one possible outcome. I have the April 1st birthday, and Jack has the April 2nd birthday. Is that okay? But another possible outcome, but only using these 2 dates, is I have the April 2nd birthday, and Jack has the April 1st birthday. These 2 are separate and distinct possible outcomes. When you choose you choose 2 days out of the year, but I can assign those 2 days differently to these 2 different people. Is that making any sense? So ordering is important because it depends on who has which day. Okay? So the answer is permutation. But this is not giving you the chances, it's giving you the number of outcomes that will make the birthdays of an entire class unique. In other words, this is telling you the number of ways that I can choose 40 cards out of 365, each card being representing each day of a year, and have a way to distribute those cards to 40 people in the class. But when you talk about chances, it's going to be the number of possible outcomes that you are interested in divided by the total number of possible outcomes. In other words, if you are not putting that restriction into this class, how many ways can we have birthdays, combinations in the class? Well, I shouldn't use combination, but how many ways can we arrange birthdays when we do not have restrictions? In other words, the entire class can have one single birthday. Okay, the class can have 2 partitions where one half of the class has one birthday, the other half can have another birthday. No restrictions whatsoever. Okay, think about that. The first student has 365 days to choose from, right? Well, that one is kind of pretty much constant for the first one. But the key here is if I don't put any restrictions, the second student also has 365 days to choose from, and so on. Okay? So this is representing the total number of outcomes without restrictions. And this is representing the number of outcomes that has the restriction put on it. Is that okay? So in this case, what we will end up with is the permutation of choosing 40 out of 365 divided by 365 to the power of 40. So it's representing a chance now because it is a number of things that can, this is the number of outcomes that we are interested in. This is the total possible number of outcomes. So it becomes a chance, a probability. This is the probability of having unique birthdays of a class of 40 people. Is that okay? Do you think this is a pretty big number? Is it close to 1 or is it not close to 1? On one hand, we have 365 choose 40. On the other side, we have 365 to the power of 40. What do you think? It's a pretty small number. So we'll go ahead and figure that out. Okay, so we'll figure out that number. So I'm going to do it step by step. The first one is to figure out the permutation of 365 choosing 40. And that is a pretty darn big number. And then the other one is 365 to the power of 40, which is also a pretty big number. So now the question is, what is the ratio between these two numbers? This number has to be less than this number, okay? There's no doubt about it. The question is, what is the ratio? So the ratio is this one divided by this one, and it is 1/10, about 11% of a chance. So with a class of 40, the chances that we have unique birthdays is only about 11%. Which means, if you look at it from the flip side, is there's a pretty good chance that at least 2 people in this class share the same birthday. A 89-ish% chance that at least two people in this class have exactly the same birthday. Did you expect that? No? So the chances of having duplicate birthdays in a class of this size is pretty high. It's not intuitive. If you think about it, it's not intuitive. Because 40 out of 365 doesn't seem like a big ratio, right? You know, it's only about, what, 1/9, right? So you would expect the chances to be, maybe 1/9 of a chance or something like that, but it's actually not that case. I don't know whether you guys know what I'm talking about. This is counterintuitive. The chances of having a duplicate birthday is actually higher than what most people expect. Yep.
So this 11% is the likelihood that there aren't any.
The 11% chance is all birthdays of class of 40 are unique. So if you subtract that from 1, which is about 89%, that would be the chance of some kind of duplicate birthday. We don't know exactly because it includes all possible ways of duplicating. Yeah, the battery just died. And this is only my first class. I still have one more class to go tonight. Let me see if there's any battery. This one is outside already. I'm thinking it probably is already used up. Okay, we'll give it a chance. I keep asking them to use rechargeable batteries, and also they do have rechargeable whiteboard markers. It's not rechargeable; it's refillable. But for some reason, they won't go for that either. Same idea. Nope, this one is not good. Well, it is, but it shows red, which means it's about gone. Okay. Well, we only have one battery here. I need 2 to make it work. All right, I guess we don't have any. Unless somebody has a cordless mouse that has a AA batteries inside, you know. Nope. Okay. See, MacGyver would have come up with a solution to this. Yep. Who has the cheapest, cell phone in this class?
Here's that.
What is that?
It's a cordless mouse with double batteries.
Does it have actual batteries inside? AA?
Triple A.
No, AAA won't work. I need AA's.
Make it work.
Well, does anyone has a soda can of something so I can actually make it into an enclosure to make it work? Okay, I guess I'll just use my voice, which is okay, because this is how I taught this class for years. It's just a little bit new to you guys, so it will get some used to. It will take some getting used to. There we go. Okay. All right. So getting back to this one, it is just we don't expect it to be this kind of ratio because it's including every single way of duplication. In other words, it's including the case where go ahead.
While you still have the spreadsheet open, could you do another column with a higher class size for comparison? I'm having a bit of trouble seeing the ratio.
Okay, so we can say, so we can use class size of 2, okay, minimum.
Okay.
1 doesn't make any sense. So we have class size of 2, 3, or do you want to go by like bigger steps? 10, 20, 40, 30 maybe? Okay, 40, okay. All right. So the equation to do this is, as the numerator, it is the permutation. 365 choose whatever the class size is. Okay, so we have permutation 365 choose this number, right? And then the denominator is going to be a power function, which is 365 to the power of the class size. Is that making any sense?
Yeah.
So when you have a class size of only 2 people, the chances of having unique birthdays is almost 1. In other words, it's pretty a slim chance that 2 people have exactly the same birthday when you only have 2 people. Kind of makes sense, right? When you have a class size of 10 people, oops. Oh, by the way, it works for 1 too. Okay, I didn't put 1 here because I thought it would be kind of silly, but let's put 1 over here and see what it's going to do. Okay. With a 1, okay, you probably can tell what it's going to do because as the numerator, it is the permutation of out of 365 choosing only 1, which is 365, right? I have 365 things to choose from. I only need to pick 1 thing. How many ways can I choose 1 thing out of 365? 365 ways. What is 365 to the power of 1? 365. 365 divided by 365 is 1, which means the chances of having a unique birthday when we have a class of 1 is 1. Does that make sense? You cannot have duplicates when you only have 1, right? Okay, so that's why these numbers actually work out in this case too. When you have a class size of 10, it is only 88%. When you have a class size of 20, it's almost just half. When you have 30, it's less than 30%. When you have a class size of 40, it is only about 11%.
50.
Want to go to 50? It's only 3% of a chance. And you can see how these numbers are not linear at all. Okay, it starts off as 1 and it drops off really fast as the number increases. But it won't get down to 0 until we get to 365. Because, 366. Because when you have 366 people in the class, and you only have 365 days to choose from, somebody's going to have a duplicate birthday, guaranteed. So it's impossible not to have duplicates in that case. Does that make any sense? But these numbers are not intuitive. In other words, this one is pretty intuitive, okay? If you only have a class of 1, there's no chance that we'll have any duplicate birthdays. Makes sense. When you have 2 people in the class, there's a pretty high chance that we do not have duplicates. Those 2 birthdays are unique. 10 is kind of like, yeah, that's kind of reasonable too. But by the time we get to 20 people, it doesn't seem to make sense anymore, because this chance seems to be lower than what we expected. When you get to 50 people, there's only a 3% chance that everybody in class has a unique birthday, which is not what most people expect. And yet we solved that problem using permutation and power. Is that okay? Now, if you want to ask the question of what if we want exactly 2 people in the class having exactly the same birthday, that actually is a harder problem to answer. Out of 40 people, okay, I only want exactly 2 people to have the same birthday. So how do we figure that out? Okay, so let me write down the question first, and then we'll take a look at how do we solve that problem. Because the whole point is not for me to give you an equation that you can memorize, so that in the future, if your employer asks you this question, like, oh, we got 100 employees here, what are the chances that all 100 employees have unique birthdays? What are the chances that your employer will ask you that question? Almost none, right? So I don't want you guys to remember the equations. I want you to understand what we are talking about so that you can solve the problem yourselves. So now the question is, out of a class of 40, what are the chances that only 2 people have the same birthday? So implying that everybody else have unique birthdays. There we go. Okay. Well, this is something that we can also solve using permutations and also using the power function. Okay. So what do you think? So the first question is, how many unique birthdays are we talking about? Out of 40 people, 2 people have exactly the same birthday. The rest of the class, the other 38 people, have unique birthdays. So how many actual birthdays are we talking about? 39. Okay, so there are 39 birthdays that we are talking about. Okay, so C365 39 is represents the number of ways we can choose 39 birthdays out of 365, where ordering is not important. So now the question is, how can I distribute these 39 birthdays amongst a class of 40? Now, because we have 40 people and 39 birthdays, we now guarantee that exactly two people will share the same birthday. Does that make any sense? So the reverse of this problem is we have to pick the unfortunate 2 people to share the same birthday out of 40 people. Does that make any sense? Because once you say, okay, these 2 people have exactly the same birthday, then the rest of the class have unique birthdays. So now the problem is, how do we choose which 2 people have exactly the same birthday? How do we figure that one out? Okay, out of a class of 40, how many ways can we pair up 2 people? That's the question. That's what we are looking for. Is it combination or is it permutation? It's combination. Why is it combination? Doesn't matter whether I choose this person first or choose that person second, because as long as these 2 people are the ones sharing the birthday, it doesn't matter because they have the same birthday, right? So it's a combination. Okay, so this is the combination of 40, choosing 2 out of 40. Okay, so how do we work this out now? So we have this number of ways to choose 39 cards out of 365, each card representing a birthday, a day out of a whole year. And then we have this many ways to choose, okay, which 2 people would have to share the same birthday. But then what about the other 38 people? How many ways can we distribute the other birthday amongst those 38 people? Would that be a order dependent, order significant problem, or order insignificant problem? Order significant, right? So we now have 39 ways to choose the shared birthday. And then we have P 38, 38. Or I should say, let's see, is it 38, 38? We have 38 factorial ways to assign the other 38 birthdays. Is that making any sense? Question? Nope. Okay. So what is going to be our numerator? Numerator, which is the number of outcomes that meets our requirement. Our requirement is out of the class of 40, we have exactly 2 people having the same birthday. The other 38 people have unique birthdays. Okay? So how do you do that calculation? Okay, the combination of 365 times choosing 39. This is how we choose which 39 days out of a whole year to begin with. Out of those 39 days, we have this many ways to choose which 2 people in the class would share exactly the same birthday, right? And then those 2 people have this many choices out of the 39 days that I have already chosen out of 365 days. And then the rest of the class has 38 factorial ways to assign the remaining 38 days out of the whole thing. But since we have 39 times 38 factorial, we can simplify that to just that. Is that making any sense? What about our denominator? Denominator. In other words, what is the total number of outcomes when we have no restrictions whatsoever? Your birthday and my birthday have absolutely no relationship. They're completely independent. 365 to the power of 40. Okay. To the power of 40. So now the ratio between these 2 numbers would be the chances. That's going to be the chances of a class of 40 having exactly 2 people sharing the same birthday. Is that okay? But does it give you an idea of how to kind of think about these problems and just kind of think in terms of, is ordering important and how many things am I choosing from and stuff like that? It's multiple stages because this one is the first stage. I'm just saying, okay, I don't really care about which 2 people have exactly the same birthday, but I know out of 40 people we have to choose 39 distinct birthdays. So I'm just worrying about, okay, out of 365 days, how many ways can I choose 39 items out of it? That's the first number. The second number has to do with which 2 people, I would say unfortunate in this case because they have to share the same birthday cake. So which 2 unfortunate people would share exactly the same birthday? Out of 40 people, there are 2, you want to choose 2, but ordering is not important in this case. So that's why we have 40 choose 2. But those 2 people have 39 days or 39 ways to choose your birthday. And then with the 38 birthdays left and 38 people left, there are 38 factorial ways to choose their birthdays. And that's why we end up with this number. So we can now do the calculation. And you'll figure out what would be the actual chances. So in the numerator, we have the combination of choosing 365 or 39 out of 365 times the number of combination of choosing 2 out of 40 times 39 factorial. So we have factorial of 39. And then the denominator is really just a power function, 365 to the power of 40. And that turns out to be 26% of it. That's the chance. So about 1/4 of the time, we will have exactly two people sharing the same birthday. Yep.
Isn't that a higher percent than we had before with just having no duplicate birthdays? I'm sorry. Okay. Yeah, no mind. Finish your life.
You mean comparing to this one? This is the chance. This is the chances of everybody having a unique birthday, and that's a lower chance than this one because the other one is representing. Okay, we only have 39 unique birthdays, so now we have two people sharing the same birthday.
Okay.
But it kind of makes sense, because now we are looking into, only choosing 39 items instead of choosing 40 items. Yep. Okay, so let's switch back here. Okay, so out of the two people who are sharing the same birthday, they have 39 ways of choosing. Well, we let them choose first, right? Doesn't matter who gets to choose first because whoever is choosing first has 39 ways to go. And then once we choose that, then we have 38, 37, and so on. But that part is ordering dependent because now we are trying to assign individual birthdays to people. So ordering is important because it depends on who gets which day, that is significant. Okay. Any other questions about this? Okay, so when you guys move on to a UC, you will have much larger classes than this. This is a big class by our standard. But when you go to UC Berkeley, some of their classes have 60 people, 70 people, right? So let's just for the sake of argument, let's say we have a class of 80 people. What are the chances that everybody has a unique birthday? We're looking at a super slim chance. But if you're not in a math class or statistics class, the professor may not know this, right? So then you can basically, when you're in trouble, you can challenge your professor to a bet. I'll bet you that the entire class does not have a unique birthday. Somebody is going to share. Somebody is sharing a birthday with somebody else in this class, and then the professor of the class go like, nah, this is only a class of 80 people. That has to be a pretty low chance. That's how you can use these numbers. Don't quote me. All right, I'll see you guys on Thursday.